We had finished last lecture with the definition of the derivative, and we discussed also the definition of the tangent line at a point where a function is differentiable. So we have two alternative definitions of the derivative at a point. The first one, this one, but of course they both say the same thing, but one is just leaves some x as a variable, and you compute the limit of f of x minus f of a divided by x minus a, and let x go to a. Another way of writing that is, since x is a number that is approaching a, it's a plus something small. So another way of writing that is to say that f prime at a will be the limit of f of a plus h minus f of a divided by h. We talked about that last time, and they're both the same thing. I mean, h is in fact x minus a if you let x be equal to a plus h. So these two definitions are used, but the one on the right is more present in the kinds of examples and in applications, and especially when we try to compute derivatives of functions such as sine, cosine, or e to the x. So the one on the right is preferred, but you should also be aware of the one on the left. So and also keep in mind that there will be problems in the exam, the first midterm, that will ask you to compute or find the derivative using the definition. So finding derivatives, using the definition. So keep in mind that for these problems, you will not be given any credit if you just tell me the rule and just tell me, say, the derivative of x squared is just 2x. You have to use definitions and arrive at the conclusion that that is in fact 2x. So let's go to some examples here. And this is what we expect you to write. I mean, you'll see problems where you're asked to do this. I mean, this is a certainty. So let's try to with first example. Suppose you have a function f of x, say is equal to 3x plus 1. What is f prime at 2, say? See, easy example. So what's the solution? So whenever you're asked to find the derivative by definition, I will tend to prefer the second formula, this one, over here. So use the h1. That's something that it makes computations much easier, so trust me on that one. So that's what we're going to do. So by definition, f prime at 2 is going to be the limit, as h approaches 0, of f of 2 plus h minus f of 2, all that divided by h. That's just the definition of it. Okay, so what is f of 2 plus h? F of 2 plus h, what do we do to what's inside f? We multiply by 3 and we add 1. So this is f of 2 plus h. F of 2 is just 3 times 2 plus 1. Remember, we plug 2 into this formula here. So wherever it says x, we plug what's inside f. And so this implies then that the quotient f of 2 plus h minus f of 2 divided by h is going to be equal to, if we expand here, we get 3 times 2 plus 3 times h for the first term, plus 1. And be careful with the sign. You have to subtract 3 times 2 plus 1, so everything is inside the parentheses. And we have to divide all of that by h. So some people open the parentheses before actually computing. This is 7. What's inside here is 7, and if you just open the parentheses, you're just subtracting 7. But something to avoid is to write this as minus 3 times 2 plus 1. or something of the sort. So you flip all the signs inside the parentheses before placing the parentheses. But this is equal to 6 plus 3h 3h plus 1 minus 7. All of that divided by h, right? So the 6 and the 1 and the 7 cancel out, and 3h divided by h is going to be 3 because we're taking the limit. Since we're taking the limit when h approaches 0, h is not equal to 0, so we're allowed to do that. So this is the quotient, f of 2 plus h minus f of 2 divided by h, which is the limit we want. This is the expression we want to take the limit of. So we have the limit when h approaches 0 of what? Of just 3, which is what we ended up with over here. Right, we computed this quotient inside the limit, and we saw that it was exactly equal to 3. And the limit of a constant is just that constant. So that's our answer. So that's how we find the derivative at a point. We will only ask you to deal with polynomials or power functions, basically, when we or radicals maybe. So a second example. So we already example. So second example, so compute the find. So f prime of x, we just say particular number, f prime of 2, where f of x is just 3 times the square root of x. Okay, so we again, f prime of 2 will be equal to just the same formula, the limit when h approaches 0. So let's change the number here. We already used 2, so let's try to compute f prime at 1 instead. So we limit of 1 plus h minus f of 1, all of that divided by h. So what is f of 1 plus h? Remember, what do? We see what's inside the parenthesis. In here is 1 plus h, so we take 3 times the square root of 1 plus h. This is what we do. So here we have an x, and on the other side we see what we do to that x. So what's inside the parenthesis? So we have a 1 plus h, so that becomes 3 square root of 1 plus h. And of course, f of 1 is 3 times the square root of 1, which is just 3. Alright, so then we can just skip a few steps. I mean, that we did before in the more elementary example. We're here, we already know that f of 1 plus h is 3 times the square root of 1 plus h, minus 3, and all that divided by h. Remember that we saw that this corresponds to f of 1 plus h. This is what's written over here. And 3 is f of 1. This is what we write over here. So we can take this is the same as taking the limit as h approaches 0 of 3. 3 is a common factor. Square root of 1 plus h minus 1 over h. 3 can be pulled outside because it's a constant. So we have 3 times the limit as when h approaches 0 of the square root of 1 plus h minus 1 over h. And to compute this limit, we go back to the first couple of weeks, and what we do is we multiply top and the bottom by the conjugate, square root of 1 plus h plus 1 divided by the square root of 1 plus h plus 1. Okay. And what we end up here in the top is equal to what's inside the square root squared, so 1 plus h minus 1, all that divided by h, the square root of 1 plus h plus 1. So the 1's cancel out here, and we have an h on the top. We can be cancelled out with the h on the bottom. So we get 3 times the limit 1 over the square root of h plus 1 plus 1, and as h approaches 0. So we write this. But now this expression inside the limit can be evaluated when h is equal to 0. This is now continuous, so it doesn't vanish when h is equal to 0. So we just get that this is the same as 3 times 1 over the square root of 0 plus 1, which is just 1 plus 1, or 3 over 2. And this is our final answer. So going back to the beginning, remember what we did was just simply substituted 1 plus h where it said x in the expression of f, subtracted f at the point, and divided by h. And we doing some algebraic manipulations that we learned a couple of weeks ago, namely multiplying by the conjugate, like we did here, we can simplify everything and arrive at the value of this derivative at this point. Okay, so as I said, we will basically ask you to compute the derivative by definition for a polynomial, for a square root, or a function like this one. Yeah, the square root times some constant, combination of these things, or also a negative power function, something that has also appeared before, something like this. So what is, this is an example we did actually last lecture, but I'm going to change actually the number which we're going to be computing the derivative. So what happens if we want to compute the derivative of f at, say, minus 2, or yeah, let's say negative numbers, so minus 1 is fine, or just, just to avoid, I want to avoid using the same numbers, so as not does not give you the impression that so the only numbers you will see. So let's try to see f of minus f prime at minus 4, say. Is equal to what? Where f of x is the function 3 over x. It's the same thing always. The definition is prime minus 4. We need to compute the limit when h approaches 0 of f of minus 4 plus h minus f of minus 4, all of that divided by h. And again, given that f of x is equal to 3 over x, so whatever we have inside f, we have to compute 3 over that in order to get the value of f. We get that f minus 4 plus h is equal to 3, and what's inside? Minus 4 plus h, so that's the value of f of minus 4 plus h, and f of minus 4 is 3 divided by what's inside here, so minus 4, which is minus 3 over 4. And this is why I wanted to use negative numbers, because this is something that can cause some problems sometimes for some students. So this is the same as the limit when h approaches 0 of f of minus 4 plus h, which is this quantity down here. So 3 divided by minus 4 plus h. And now we have to be careful. So it's minus what? F of minus 4, but f of minus 4 is minus 3 over 4. So it's that. And then we'll divide everything by h. Now this is equal to the limit when h approaches 0 of 3 over minus 4 plus h. And minus minus, this is why I wanted to use negative numbers, is going to be plus 3 over 4. All of that divided by h. Again, yeah, we need to find a common factor, so we cross multiply. 3 times 4, and 3 times minus 4 plus h. And we get, this is 12 plus 3 times minus 4 plus h. Yeah, the 12 comes from actually multiplying 3 times 4. And then we divide by 4 times minus 4 plus h. 4 times minus 4 plus h. This is just basic arithmetic with fractions. And we have a fraction over a fraction. This is something we mentioned in the past, in case you forgot. So this becomes the same as, well, 12. 3 times 4, 12, plus 3 times minus 4, which is minus 12, plus 3 times h, all of that divided, and then, this is what I said to pay attention to, 4 times minus 4 plus h, and all of that divided, multiplied by h. So this comes here because h is the same as h over 1. And remember, we had that rule we used also last time. So if we have a over b divided by c, this is the same as a over b times c. Okay. And in general, a over b divided by c over d is a over b times d over c. And this is the only thing we've used here. Now, going back to the limit we want to compute, we have a 12, a minus 12, that's a 0. We end up with a 3h, and that's the only thing remaining in the top. So the h's here can be cancelled out. So we have to compute the limit when h approaches 0 of 3 over 4 times minus 4 plus h. But if we look at the quantity we have inside, it is a well-defined expression, so we can simply plug in 0. We can use the substitution method, and we get, when we plug in h equals 0, we get minus 16, and this is the same as minus 3 over 16. That will be our final answer. So going back to the beginning, we trusted our definition for the derivative, and as I said, whenever you're asked to find these things, try to use the first expression. The second expression for the derivative involving h, because that will make computations easier. Sometimes it will be unavoidable because they will actually ask you to check whether some expression is the derivative, and it's not going to be given to you as a limit involving h, but just the first, it's going to be the limit in the first form. But when you're given the choice, try to use the second form. And here we just plug in everything. We substituted everything for this particular function, and at this particular point here, the point is minus 4. We had to be careful in this step here not to mess up the signs of we were dealing with negative numbers, so minus minus, we have to keep in mind that will be positive, and then we handle these fractions here carefully, and after all the cancellations, we could just simply you ended up with an expression for which we could evaluate or plug in the value 0, and we obtained the limit, which is minus 3 over 16. And so that's another kind of problem that we may be asked to So, I mean, they're all the same kind of so far. So the point is that you may be asked to compute the derivative by hand. That means using the definition of polynomial functions, or some functions like this one involving the square root, or power functions, negative power functions, like 1 over x, 1 over x squared, which is the case for this function. Okay, so we go over this kind of problems carefully. I will have a list of prepared problems from the book, because there are other ways in which you can be asked to apply the definition of the derivative. A few more examples are going to be included here at the end of this video, but I'm going to avoid making it too long. But so fourth example. So given f of x for x plus 1, say, what expression corresponds to f prime at 5, say, and you're given two options. So let's try to choose maybe a smaller number, 1/2, because we can, I mean, don't get used to just dealing with whole numbers, with natural numbers. And they may give you two options. So first one is the limit as x approaches 1 over 2 of 4x plus 1 minus 3 over x minus 1 over 2. The second one may be the limit when h approaches 0 of 4 times 1 over 2 plus 4 times h plus 1 minus 3, all that divided by h. So what would be your answer here? Well, the answer is both of them. This is just the definition of the derivative. And this is the second one. Second definition. The derivative. So the answer is both. And to make matters worse, I mean, in fact, I tried to make it more explicit here, but they could have asked you also, you see, because once you write down the definition using the first expression for the derivative or the second one, you notice here that you can simplify 1 and minus 3, maybe you can subtract that and end up with something like the limit when x approaches 1/2 of say 2 times 4x minus 2 divided by x minus 1. And you'll see that if you manipulate this expression here, that is exactly the same thing as what we have here as well. So it's just 1 minus 3 is minus 2. And the 2 here, I mean, the expression at the bottom can be written as 2x minus 1. Sorry, so this is 2x minus 1. 2x minus 1 divided by 2, which can be brought into this expression by using the same rule about fractions that we used before. Okay, so you have to be very careful about that. So just proceed and write down using the first definition of the derivative. If you see an x, if you see an h, try to use the second one. But then manipulate it further to check that among the options, I mean, you're not missing one of the options, which may be correct. For the second one, for instance, we can simplify things more. So the second expression is actually also equivalent to, and now this is the limit when h approaches 0 of, and we can take the 4 times 1 over 2 is 2, so we get 4h, and inside the parenthesis plus 3, but then minus 3 is just 4h. Something that looks silly here, but this expression, where you just need to simplify the h's, is also the derivative of this function at the point 1 over 2. This is completely equivalent to this. Okay? So just keep that in mind. So this expression here is just the same thing as this quotient. Okay, and so that's the first part. I mean, we'll go over a few more examples in the next video. And then we'll continue with the rest of the material for the week. I mean, as I said, I wanted to focus on problems, and more specifically on problems that you are bound to see in the exam for the first midterm that it comes next week. So, yeah. Thanks for your attention, and I'll see you in the next video.